Welcome to the video lecture on transformations. Today we're going to talk about how you can take some basic functions and shift them up, down, left, right, flip them over, and compress them or stretch them vertically or horizontally. So there's a lot of different transformations that we're going to talk about today. Now before we even begin, I want to remind you that we do have something called a function library. This is a PDF file that has some of our basic functions on it that you are expected to know how to graph by hand. So for example, the squaring function x squared, you should know what its pattern is, the cubic function, the square root function, absolute values, reciprocals, and grazed integer functions. So we will be referring to this basic function library throughout today's lecture. So let's start off with one of our basic transformations. Sometimes this one is called a translation, and what we're going to see is how our graph will shift if we add a constant off to the side. So what I want to do is go ahead on our graphing calculator. We want to plot these three different equations. So let's go to y equals, and we're going to type in x squared in y1. We're going to type in x squared plus 2 in y2, and we're going to type in x squared minus 2 in y3. I'm just going to do a standard window, so zoom standard. There's x squared plus 2, and there's x squared minus 2. So you have to keep track which one is which, but the one in the middle was the original one. The one through the origin was x squared. The one above was x squared plus 2, and the one below was x squared minus 2. And you can see from the y-intercepts that x squared plus 2 has a y-intercept at positive 2, and x squared minus 2 has a y-intercept at negative 2. So what kind of shift vertically did occur for this graph x squared? When we added 2, what happened to the graph? It moved up 2 units. When we subtracted 2, what happened to the graph? It shifted down 2 units. So this is called a vertical shift, and if we are adding a positive constant off to the side, then this is going to be a shift up k units. If we subtract a constant off to the side, then this is going to be a shift down k units. So a vertical shift, up or down, occurs when the constant is being added off to the side. Now that's important to notice because in the next examples, this time we're going to still add and subtract, but this time we're going to be adding and subtracting a constant inside of our parentheses. So if you look at these two examples, we have a minus 3 and a plus 2 right next to that x. So let's go back to our y equals, and I'm going to leave x squared in my y1, but this time in y2 and y3, I'm going to type in parentheses x minus 3 quantity squared and parentheses x plus 2 quantity squared. And maybe to differentiate these graphs a little bit, I'm going to change the style type. So if I arrow over to the left, next to that y sub 3, you can see that little symbol is flashing, and let's go ahead and change it. I'll go ahead and make this one that solid line. If I arrow up, let's hit enter a couple times, and I am going to see if I can find there we go. I'm looking for that little dotted line. So when it graphs x squared, it's just going to be a connected line. When it graphs y2, it's going to be a dotted line. And when it graphs y3, it's going to be a solid line. So that way we'll be able to tell the difference between the three graphs. So we still are on a standard window, so I'm just going to go ahead and hit graph. There's x squared. There's x minus 3, and the solid one was x plus 2 quantity squared. So I want you to see the difference between these three graphs. The one in the middle, centered at the origin, was x squared, and the dotted line off to the right here is x minus 3 quantity squared. And if you can kind of see, it's a little bit tricky to see, but where is it hitting that x-axis? Where is its x-intercept? Well, when x is positive 3, this has its vertex. So this is going to have caused my original graph x squared to shift to the right 3 units. So this one goes right 3, even though we had a minus inside the parentheses. Normally when you think minus, you probably would think go left, because that's the negative direction, but here it's opposite. Here we actually go to the right. And similarly for x plus 2, that's this solid graph right here, this bold one, it shifted to the left 2 units. So again, it's going backwards from what you would expect. You needed an x-intercept of -2 to make this quantity go to 0. So horizontal shifts, which are moving to the right and to the left, go backwards from what you would expect. Let me make a note of that. So horizontal shifts go in the opposite direction from what you would expect. So if we see a plus k inside of your parentheses next to that x, we would probably think positive, shift right, but this is actually going to go in the opposite direction, left. So if you see a plus k, then this is going to be a horizontal shift to the left k units. If we see a minus k, we would probably think go left in the negative direction, but this actually goes right k units. So when the number is inside the parentheses, that's a horizontal shift. When the number is outside of the parentheses, off to the side, like in the previous examples we did, then that's a vertical shift. And in the vertical shifts, you go in the direction that you would think. In the horizontal shifts, you go in the opposite direction from what you would think. So let's try an example where we put these in action. Say that I have y equals x plus 4 quantity squared minus 5. First, we want to identify what are the transformations that have occurred in this equation from a basic x squared graph. So if you look at this, you see that plus 4 inside the parentheses, and you see that minus 5 outside of the parentheses. When it's inside the parentheses, that's always in the horizontal direction. So this is going to be a horizontal shift, and it's going to go backwards from what we would expect. So plus 4 means we're actually going to go left 4 units. When the constant is off to the side, outside of the parentheses and outside of that square, then that's going to be a vertical shift in the direction that you would expect. So a minus 5 means we're going to go down 5 units. So what we want to do is graph our normal x squared graph, and we want to shift it so that the vertex gets shifted left 4 and down 5. So if we take a look at our graph here, we have the origin right here in the middle, which is normally where the vertex would be, but now it's going to get shifted to the left 4 units, and then it's going to get shifted down 5 from there. So to the left 4, down 5, so the vertex is now at -4 for x, -5 for y. And then to complete the graph, and you should be able to do this by hand, I'm just going to use our normal pattern for a parabola. If there's no stretching involved, then the normal parabola pattern is over 1, up 1 from the vertex, and then over 1, up 3 from the vertex. And that's going to give us a couple of side points. So if we know where our vertex is, I'm going to go over 1, up 1, to the left and to the right, and then I'm going to go over 1, up 3, to the left and to the right. And that gives you 5 good points on your graph so that you can draw a nice parabola. Okay, so horizontal shifts are when the constant is inside the parentheses. Vertical shifts are when the constant is outside of the parentheses. Now let's take a look at some of the vertical and horizontal compressions and stretches, and these are kind of tricky. So we're going to take a look at an example where we are multiplying our function on the outside by a constant or possibly by a fraction. So anytime you're doing something to the outside of the function, that's going to cause a vertical change, either a vertical shift up or down, like in the last few examples, or a vertical stretch or compression, which is what we're going to see in these examples here. So let's go ahead and go to our calculator, and in our y equals, I'm going to clear out my equations, and in y1 I'm going to type in the absolute value of x. Now if you have a graphing calculator, this absolute value function is on your calculator, but it's hidden under the math key. So you want to be in your y1 equals screen, then you're going to hit math, and you're going to arrow over to where it says NUM for num. So arrow over once, and right at the top there, number 1 is ABS, and that stands for absolute value. So I'm going to go ahead and hit enter, and I just want the absolute value of x, close my parentheses. Then in y2, I'm going to do 2 times the absolute value function. So 2, then hit math, arrow to the right once to get to num, and option number 1 is ABS. And I want 2 times the absolute value of x. And then in y3, I'm going to do 1/2, so 1 divided by 2, hit math, arrow over, option 1, and I want absolute value of x. Let's go ahead and change the style type of the graph. So let's make y3 bold again, and let's make y2 the dotted line. So just keep hitting enter until you see those dots. And I'm just going to hit graph. So here's absolute value, and then we see our other two. So this top one here is the 2 times absolute value of x, and the bold one is the 1/2 times absolute value of x. So if you think in terms of stretches and compressions, which one of these got stretched up higher? Well, obviously it's going to be the graph that's now steeper or lies inside. So the 2 times the absolute value of x is called a vertical stretch by a factor of 2. And basically all we did is we took all the normal y values that would be on the absolute value function, and we took all these normal y values and we multiplied them by 2. So we doubled them all. So they are all now twice as high as they used to be, which is why this graph lies higher and is steeper than it used to be. Then for the absolute value graph that's bold here, that's your 1/2. And in that case, what we did is we took all of these absolute value, normal y values, and we're taking half of them. So now they're half as big as they used to be. So this is called a vertical compression by a factor of 1/2. So they're half the height that they used to be. And what you'll see on a graph typically is that when you have a stretch, a vertical stretch, that's going to make your graph get steeper and usually higher and closer to that y-axis. And if you have a compression, that's going to push that graph down closer to the x-axis and make it get flatter. So how do you remember which one is which? Well, when the constant out front, this a value that's being multiplied by your function, if that a is bigger than 1, then that is going to be a vertical stretch by a factor of a. If the a out front is between 0 and 1, which just means that it's a fraction, so anytime you multiply by a fraction on the outside, then that's going to be called a vertical compression. And that's going to make your graph get flatter and push it down, versus the vertical stretch, which makes your graph get steeper and pushes it up. Okay? So now we're going to do something similar to that, but this time instead of multiplying the outside of the function, multiplying those y values by a constant, now we're going to multiply the x values by a constant. So you'll see the difference because this time the 2 and the 1/2 that we're multiplying by are right next to that x, and they're inside of the parentheses. And anytime you're doing something inside of the parentheses times that x, that's always going to be causing a horizontal change, either a shift left or right, or in this case, a horizontal stretch or a horizontal compression. Now, we probably aren't too familiar in this class with how to graph sine curves, and that's okay because we're going to make our calculator do all the work for us. So for this one, the horizontal stretches and compressions are just a little bit more obvious to see when you're looking at trigonometric functions, so that's why I'm using these examples. But I wouldn't expect you to be able to graph a sine curve on your own yet. You wouldn't know how to do that until you talk about trigonometry. So for these examples, I would expect you just to do it solely on your calculator. So let's go ahead and go to our y equals. Let's clear these out. And in y1, I'm going to type in the sine function. So I'm going to do sine of x and close the parentheses. And then in y2, I'm going to do sine of 2x, close the parentheses. And then in y3, I'm going to hit the sine button. 1 divided by 2, or 1/2 of x, close the parentheses. And I'm going to change my style type. So y3 will be the bold one again, and y2 will be the dotted line. Now, a couple of things about graphing trig functions. You need to be in a certain mode. So if you will take a moment here to click on your mode button, what you want to make sure of is that you're in radian mode, which this one is. Usually that's the default. But if for some reason your calculator was set on degrees, if it was set on degrees and the degree was highlighted, then you would just arrow over to radians, hit enter to make sure that it's highlighted. Now, the other thing about graphing trig functions is you really need to have a good window to be able to see the sine curves very nicely. And if you go to zoom, there's a nice easy way to do that, and that's option 7 here, zoom trig. So I'm just going to go ahead and hit 7, and that'll give me a nice window to see my trig functions in. So here was the sine curve, the dotted one was sine of 2x, and this bold one is sine of 1/2 x. So take a look at these 3 different graphs. Okay, so we have our normal sine curve, which had many ups and downs, and then we had our sine of 2x, which was this dashed one, and then we had our bold one. So just to make it a little less confusing, I'm going to turn off the bold one for a moment, and we're just going to look at the original sine curve and the sine of 2x. So we have to watch carefully so that we see which one is which. Here's the normal sine curve, and then here's the sine of 2x. Now hopefully you can see that we've sort of doubled up how many cycles this graph goes through. Instead of just going up and down and then up and down like the normal sine curve does, now we're going up, down, up, down, up, down, up, down. So we've doubled up how many cycles we pass through. And the width of those cycles is much narrower than it was before. So normally this one cycle, or what we call period of sine, it goes up and then goes down from 0 to the end of this window, and now it's going through 2 of those cycles in that same width. So what that's called is a horizontal compression by a factor of 1/2. So we're now able to do twice as many cycles as we were before because we've shortened up horizontally how much the graph goes through. So the graph period gets through a cycle in half the width that it did before. So we've compressed that width by half. Now let's go back to y equals, and I'm going to turn off y2 by hitting enter on that equal sign, and I'm going to turn back on y3. So highlight y1 and y3, hit graph, here's the normal sine curve, and then we've got sine of 1/2 x. So again, normally the sine curve would go up and go down, and in this first quadrant here, now sine of 1/2 is just going up. It hasn't even completed one full cycle yet. So we've sort of stretched out that width, so it's not even completing the cycle in the normal width that it would. If we were to extend this window horizontally, then you could probably imagine seeing the bottom half of that cycle completed, so that it's going to take twice the width to complete this cycle than it normally would have. So when you put in this 1/2, now what we have is that the graph has been horizontally stretched by a factor of 2. So if the constant on the inside, this a, being multiplied by x, is a number that's bigger than 1, then this is going to be a horizontal compression by a factor of 1 over a. So remember up here when we had our 2 times x, we actually compressed this to a factor of 1/2. So we got through one cycle in half the amount of time that we did before. If the a inside is a fraction that you're multiplying by, then that actually stretches the graph horizontally by a factor of a. Oops, this is a typo here. Sorry, this should say a right there. That was a mistake on the notes. So this is a horizontal stretch by a factor of a. So before, when we had this 1/2 in here, what happened to this bold graph is we stretched out that cycle to twice its normal size. So even though we had a 1/2 here, we doubled its cycle length. So these are going to occur kind of in reciprocals. So the number that you see inside being multiplied by x, you actually want the reciprocal of that over here on the right hand side. So when I have a 2 inside, it's opposite of what you would expect. It's going to be a compression by a factor of 1/2, and when I have a 1/2 inside, you use its reciprocal, and again, think opposite of what you would expect. Even though we have a 1/2, that actually means that we're stretching it by a factor of 2. So just like we had earlier on in the notes on the previous page, horizontal shifts go in opposite direction from what you would expect. That's true for these horizontal compressions and stretches as well. They also go sort of opposite of what you would expect. So one last time, if the constant is bigger than 1, that's going to cause a horizontal compression by a factor of 1 over a. And if the a inside is a fraction, then that's going to cause a horizontal stretch by a factor of a. Okay, so let's try putting this into action. So here's the graph of a function f of x. I'm not going to tell you a formula or anything like that. All we have is its graph. So let's identify a couple of the key coordinates on this graph. This is going to be x value pi over 2 and y value 1. This point right here is pi for x, 0 for y. This point down here is 3 pi over 2 for x, negative 1 for y, and this is 2 pi, comma 0, and this is obviously 0, 0. So those are some of our key coordinates for our function f. Now the first thing we want to do is we want to take 2 times this function, and we want to draw what this new graph would look like. So first of all, let's identify in advance what multiplying by 2 does. When it's multiplying on the outside of your function, outside of the parentheses, remember that that's a vertical change, and because we're multiplying, this is called a vertical stretch. Verticals go in the direction that you would expect. So if we multiply by 2, we're stretching it by a factor of 2. So what that means is all of these old y values on the original function f are now going to get doubled. They're going to get stretched up higher and multiplied by 2. So let's think about what that's going to mean. And let me put some unit marks here on my graph. We're not doing anything to the x's because this is a vertical stretch that we're doing. So we're only changing the y values. So for example, if I take this original dot, which is normally at 0, 0, all we're going to do is take that y value, which is 0, and we're going to stretch it by 2. We're going to multiply it by 2. And when you take 0 and you multiply it by 2, it stays 0. So this is going to stay at the origin. But if I go to this dot up here, which is at pi over 2 comma 1, it has as its y value 1, and now what we're going to do is stretch that by a factor of 2 by multiplying it by 2. So 1 times 2 becomes 2. So the x value won't change. The x value is still at pi over 2, but now instead of going 1 high, we're going to go 2 high. So it's now up here. If we go to pi comma 0, this has a y value of 0, so when I multiply that by 2, that's going to stay 0, and the x value is not changing. If I go to this dot, 3 pi over 2 comma negative 1, it has a y value of negative 1. If I multiply that by 2, now it's going to go down to negative 2. So the x value is still 3 pi over 2, but the y value is at negative 2. And finally, 2 pi comma 0, if I double that 0, it stays 0. So if we connect these dots with a curve that has a similar shape to what we had, it's going to look very similar, but you'll see that these peaks and valleys, these maxes and mins, are now higher and lower than before. So we've just sort of stretched up this graph vertically by pulling those peaks and those valleys lower and higher than they were before. So that's what the new graph would look like. So then let's go to this next example. This time look at the position of that 3. That 3 is on the inside of your parentheses, so that's going to make it a horizontal transformation. It's being multiplied, so if you're multiplying, that's going to be either a stretch or a compression. And because it's in the horizontal direction, that's always opposite of what you might expect. So if you think about 3 times your x, you might expect it to multiply your x's by 3, but it's actually the opposite of that. It's that reciprocal relationship. So instead of multiplying your x's by 3, we're actually going to compress our x's by 1/3. So this is a horizontal compression by a factor of 1/3. So what that's going to do is it's going to multiply all the original x's by 1/3. And this is only happening to the x's. So we're not going to change our y's or our heights at all. All we're doing is we're changing the x's. So for example, I like to work with zeros first if I can. Let's take this 0 right here, which is normally at pi comma 0, that middle point of this cycle. Think about what that point is going to change to. If right now the x value is pi, what we're going to do to it, because of this 3 here, is we need to compress it by 1/3. So we need to take 1/3 of that pi. So what's 1/3 of pi? Pi over 3. So here's pi, and let me cut that into thirds. So this would be pi over 3. This would be 2 pi over 3. 2 pi would be over here. Let me cut this distance into thirds as well. So I would have something like that. So normally this dot is at pi comma 0, and now I'm going to take 1/3 of that x value, which becomes pi over 3, and I'm not changing the y coordinate at all. So the height is still going to stay 0, but instead of hitting 0 at pi, now it's going to hit 0 at pi over 3. So I didn't change the y stayed 0, I just took 1/3 of the x. So this dot right here becomes that dot. Okay? Let's try it again for some other ones, some other points. So if I take this dot right here, let me do the other zeros that I see. If I take this x value and I take 1/3 of it, 1/3 of 2 pi is just 2 pi over 3. So I'm going to take that x, which was normally at 2 pi, and I'm going to cut it in 1/3. I'm going to compress it by 1/3, but the y value is going to stay 0. So this 2 pi shifts horizontally, compressed down to 2 pi over 3, and the y value is staying 0. So this dot becomes that one, and this one was here. Okay, let's do the other 0 that we have, and that was at the origin. So if I take this dot right here, which is at normally x value of 0, I'm going to take that x value of 0, multiply it by 1/3. 1/3 of 0 stays 0, so this point is also going to stay at 0, and the height stays at 0. So this point goes right there. Okay, now let's find out a couple of our peaks and valleys. So this x value is pi over 2, and we need to take 1/3 of it. So I'm going to take 1/3 of pi over 2. What's 1/3 of pi over 2? We'll just do top times top, which is pi, over bottom times bottom, which is 6. Where is pi over 6? Well, it's halfway between 0 and pi over 3, so it's right here. Remember, we're not changing the y coordinate, so instead of having an x value at pi over 2, now we're looking at an x value of pi over 6, but the y value stays 1. So this is going to be at an x value of pi over 6 and a y value of 1. So this peak goes to that dot right there. Okay, now let's do our valley. So our valley is down here, and we need to do 1/3 of 3 pi over 2. The 3's are going to cancel out, giving me just pi over 2. And where is pi over 2? Well, it's right in between pi over 3 and 2 pi over 3. It's right in the middle. So here's our halfway point, and our y value was -1 before, and it's going to stay -1. So here is that new dot. Oops, sorry about that. So here's my dot, and let's connect them, and you'll see this shape appear. So we started here, we go up, we go down, and then we go back up again. So this cycle, which normally spanned all this distance from 0 to 2 pi, now it goes from 0 to 2 pi over 3. So we compressed this whole distance, this horizontal distance, by a factor of 1/3. What's 1/3 of 2 pi? It's 2 pi over 3. So that's why this cycle is stopping at 2 pi over 3. We took this whole horizontal distance here, and we chopped it into 1/3 of that distance. So if I were to continue this graph and keep drawing, I'd be able to fit 3 full cycles in this distance from 0 to 2 pi, whereas in the original graph I could only fit 1 cycle from 0 to 2 pi. So I'm compressing that cycle width to a factor of 1/3. Okay, so horizontal compressions or stretches, you're multiplying the x value by the reciprocal. For vertical stretches and compressions, you're multiplying the y value by exactly that constant that's out front. So those are kind of tricky to deal with. Alright, let's switch gears a little bit and talk about our last type of transformations that we're going to talk about, and those are reflections. So this time we're going to graph square root of x. Let's go back to our y equals. I'm going to clear out my graphs here, and I'm going to type in square root of x, and then in y2 let's type in negative. Don't use the subtraction button, use the little negative button, square root of x. And let's just graph this one first. I'll go ahead and do y3 in a moment, but let's just see what the negative on the outside of the square root does to our graph. And remember, we're in this weird trig window, so make sure you go to zoom and hit zoom standard to get back to a normal window. So the graph on top, and let me go back here and change my style so you can see the difference. Let me make this bold. The one on top is square root of x. The one on the bottom is negative square root of x. So what just happened here? What kind of reflection did we just see happen? Well, the graph flipped over that x-axis. So when the negative is on the outside of your function, that's a vertical reflection over the x-axis. Now let's go to our y equals. I'm going to turn this graph off, and I'm going to, in y3, type in square root of negative x, and I'll make this one bold, and let's hit graph. So there's our square root, and now here's square root of negative x. So what kind of reflection is this? Well, we took our normal graph and we reflected it over the y-axis. So when the negative is inside of the radical, then this causes us to have a horizontal reflection over the y-axis. So just as before, and this is very consistent, when the number is outside of your function, whether it's a negative, a constant, a fraction, whatever, when it's outside of your fraction, that's always a vertical change. And in this case, it's going to be a vertical reflection over the x-axis. When the negative is inside of the parentheses next to your x, that's going to cause a horizontal change, and this would be a horizontal reflection over the y-axis. So in your D2L, there should be a PDF file labeled Summary of Transformations. This is what it looks like. And it just lists all of these different types of transformations that we've talked about and what they might look like for some of our more common functions like x squareds, square root of x's, absolute values, and greatest integers. So adding or subtracting a number off to the side is a vertical translation up or down. Adding or subtracting a's would be shifts left or right. X-axis reflections have the minus on the outside. Y-axis reflections have the minus on the inside. Vertical stretches multiply by an a on the outside. Vertical compressions multiply by a fraction on the outside. Horizontal stretches have a fraction being multiplied on the inside, and horizontal compressions have a number being multiplied on the inside. And in terms of which is more important, we usually say that reflections, stretches, and compressions, anything that requires you to multiply, those all would rank higher in priority versus any time that you add or subtract off to the side or inside those parentheses, like those shifts left, right, up, and down, those would have a lesser priority. So this is just a summary of all the different transformations that you're responsible for knowing. So you might want to print this off and keep it handy when you're doing your homework. Alright, let's practice. So these next examples are all pretty typical of something you would be expected to do on tests and quizzes. We have y equals negative absolute value of x plus 3 minus 2. And you would be expected to graph this by hand without a calculator and list what kind of transformations are being applied. So if we take a look at this function, first we have this negative that we're multiplying by on the outside. So in terms of order of operations, you multiply ranking or multiplying ranks higher than addition or subtraction. So this negative on the outside is going to probably be the first transformation that you'd want to list, and because it's on the outside of the function, It's a vertical reflection over that x-axis. Then the +3 on the inside, remember when it's on the inside, that's a horizontal change, and this is on the inside, so it's a horizontal shift, and it's going to go backwards from what we would expect. So a +3 you think go right, but it actually is going to go left 3 units. And finally, the -2 on the outside of the function, when it's outside, it's a vertical change. So this is going to be a vertical shift, and because it's minus, that means we're going to go down 2 units. So let's put this all together into our graph. And in order to graph this by hand, you have to know the basic shape of an absolute value. And you should know that that's a V shape. You want to find where that vertex is first, and then the pattern is over 1, up 1, over 1, up 1, to the left and to the right. So that part of it does need to be memorized. So where is our vertex going to be? Here's the origin. Normally it would be at the origin, but what we're doing is we're shifting left 3 units, and then we're going down 2 units, so there is our new vertex. Because we have this reflection, instead of going up and pointing in as a V going up, this is going to flip you over that x-axis, and it's actually going to be a V going down. So the shift left and right and down or up just moves that vertex, and then the reflection tells you which way to point. So we want to point down, so I'm going to use my pattern and go over 1, down 1, over 1, down 1, over 1, down 1, over 1, down 1, until you get a couple of side points and you get that upside down V shape. Okay, let's try the next one. So on this one we have y equals the square root of -x plus 1. So a couple of the transformations that I see, I've got a negative on the inside, so if it's on the inside, that's going to be a horizontal type of reflection. And if it's horizontal, then that means it's going to be a reflection over the y-axis. Then we have this +1 on the side, which is going to be a vertical shift, because it's on the outside, and it's going to be a vertical shift up 1 unit. So now what we need to do is remember our graph of square root of x. You need to know how to graph that by hand, and you need to know what its normal pattern would be. So normally square root of x is started at the origin, and then you would go up 1 over 1, and then you would go up 1 over 3. So up 1 over 1, up 1 over 3 is the normal pattern. But we are reflecting over the y-axis. So instead of pointing towards the right, we're going to want to point towards the left. So we'd go up 1, left 1, up 1, left 3. Then we have this vertical shift up 1 as well. So instead of starting at the origin, this is going to start up 1 unit. So right here at 0, 1, and then I'm going to point towards the left using my pattern. So up 1, left 1, up 1, left 3. So here's what my final graph would look like. Okay, this next example with these double bars, this is called the greatest integer function, and you would be expected to know what the graph of this looks like. And it is a step function. And what it means, or what it stands for, is it's asking for the greatest integer. If you put in an x, what's the greatest integer less than or equal to that x value? So for example, the greatest integer of a half, the greatest integer that's less than or equal to a half would be just 0. The greatest integer of 1 is 1 itself. So if you have an integer inside here, you just get back that integer. But if you have a fraction inside, then you take the integer that's just below it, just to the left of it. So this step function looks like this. It's little tiny steps of width 1, and they go up by 1 unit each time as well. And notice that the number on the endpoint on the left is a solid dot, because the greatest integer of 1 is 1, so that's this dot right here. But then the greatest integer of 2, you have to jump up to a height of 2. So you end up with steps of width 1 that jump up by a height of 1 each time. The left endpoint should be closed, the right endpoint should be open. So if we have the greatest integer of 1/2 x, what does this 1/2 do? Because it's being multiplied by the x on the inside, that's going to be a horizontal change. And remember, this is going to be either a stretch or a compression, because we're multiplying. And because it's in the horizontal direction, it's going to be sort of opposite of what we would expect. We're actually going to use the reciprocal. So this is going to be a horizontal stretch by a factor of 2. You're using that reciprocal. So what that means is that if normally our steps have a width of 1, we're going to stretch that out horizontally so that each step now has a width of 2. So you can imagine that this very first step, normally it would just go from 0 to 1. But what we're going to do is we're going to stretch that out. Still going to start at the origin, but now it's going to stretch out and go all the way to 2. We're not changing the y's here at all. So each of these steps is going to bump up 1 unit each time. So this next one here, you can see, would be just at a height of 1, but it's going to have a width of 2. Go up 1 unit higher and have a width of 2. Go 1 unit lower, have a width of 2. 1 unit lower, but a width of 2. And all those left endpoints should be solid. All those right endpoints should be open. None of these steps should overlap. So you're going by all those even integers, 0 to 2, then 2 to 4, then 4 to 6, -2 to 0, -4 to -2, and so on. So your x's aren't overlapping at all, and the y's are going up by 1 each time. Alright, let's try another one. This time we have a quadratic because I see that square in there. So we want to first identify what kind of transformations we have. And the first thing I see is this 2 on the outside. It's on the outside of the function, so that's a vertical change. And because we're multiplying by it, that's going to be a vertical stretch. So this is a vertical stretch by a factor of 2. The -1 on the inside, remember, if it's on the inside, that's horizontal. So this is going to be a horizontal translation. And because it's a -1, we're actually going to go right 1. So this is a horizontal shift, right 1 unit. And then finally we have that -3 on the outside, so we're back to being a vertical change. And this is going to be a vertical shift. Since it's a -3, that means we're going to go down 3 units. So normally our parabola has this U shape with the vertex at the origin, but if there is a stretch involved, like this 2, this factor of 2 that we have, that's going to stretch our pattern. So instead of going over 1, up 1, over 1, up 1 on either side, and then over 1, up 3, now we're going to multiply those vertical changes by this 2. So we're going to go over 1, not up 1, but over 1, up 1 times 2. And then we're going to take this over 1, up 3, which it normally would be, and we're going to multiply that 3 by 2. So sometimes what I tell students in general is if you have y equals any a being multiplied out front of your x squared, the pattern to remember is over 1 up a, over 1 up 3 times a, and so on. So you're multiplying this vertical stretch or compression by the normal pattern. So we're going to go over 1 up 2, over 1 up 6, etc. Before I even use that stretch, however, we need to place where the vertex should go, and that comes from the horizontal shift and the vertical shift. So we want to go right 1 and down 3. So the vertex is going to be at positive 1, negative 3. Once we know where that vertex should start, then we're going to use our pattern of going over 1 up A, so in this case over 1 up 2 to the left and to the right, and then over 1 up 3 times A, or 3 times 2 would be 6. So I'm going to go over 1 up 6 and put a dot to the left and to the right. And when you connect these with that U shape, your parabola should look a little skinnier or a little bit more narrow than normal because we're stretching this graph up higher, so it's not quite as wide as it used to be. Okay, what we're going to talk about a lot in the next several examples is how to identify correctly all the different transformations in your function. And what we're going to do is we're going to convert all of our functions into a very specific factored form so that we can correctly identify what kind of vertical stretch or compression we have, what kind of horizontal stretch or compression do we have, what horizontal shift do we have, and what vertical shift do we have. In order to identify those correctly, you want your function to look like this form right here. So it's very, very factored. So you're going to have a constant way out front. If there is a constant A way out front, then that's going to cause you to have a vertical stretch or compression. If A is bigger than 1, it's a stretch. If A is a fraction, it's a compression. Then on the inside of your parentheses, and this is the important part, if you have any x with a coefficient, then any coefficient in front of the x has to be factored out first, and that's going to become this b that we see right here. That's being multiplied by your x, so that's a horizontal change. If b is bigger than 1, then that actually becomes a compression. If b is a fraction, then that becomes a stretch. Then inside your parentheses next to that x, you may have a constant being added or subtracted. That's going to cause us to have a horizontal translation. And then you will have a d off to the side, and that's going to be our vertical translation. So we just have to be really careful about how we look at these so that we can get the proper translations involved. And it looks like my writing here got a little bit overlapped. So let me recopy this so we can see it better. And I'll erase this right here. So here's what my function looks like, and we want to correctly identify all of our transformations. So let's take a peek at the inside of our absolute value to begin with. Now there's a common mistake on these problems. When you look inside these absolute values, a lot of times what students will see is this -3 being subtracted from the x. And we usually think, oh, if there's something being subtracted next to that x inside of these absolute values, then your first guess might be that this is going to be a horizontal shift to the right 3 units. But that's actually wrong, because we have this 4 coefficient in front of the x, and we haven't properly factored it out yet to identify what kind of horizontal stretch or compression we have, and that will affect whether or not we have a horizontal shift and by how much. So before you can correctly identify what your horizontal shift is, anytime you see a coefficient in front of x, you need to factor it out from everything inside these absolute values. So this is how you would do that. You would just take your 4, and then in parentheses, you're going to write down what would be left if you were to factor it out. Well, obviously we're going to be left with just an x, but this is a little bit tricky. What would have to be right here so that if I were to redistribute my 4, I would get back 3. So 4 times what gives you 3? 4 times what gives you 3? If you were to solve for this question mark, we'd have to divide by 4. So what we're missing is a 3/4 in this little circle. So it's going to look like this. X minus 3/4 in parentheses. And if you were to redistribute 4 times 3/4, the 4's cancel, giving you back that 3. Now you're saying, well, why do I need to do this? Well, the reason you need to do this is because then this 4, because it's on the inside, that's a horizontal change, and because it's bigger than 1, it's actually going to be a compression. So this is going to cause a horizontal compression by a factor of 1/4. And then, because we factored out that compression factor, what that means is that in terms of horizontal shifts or horizontal translations, which is what this number represents since it's next to the x, this is going to be a horizontal shift right, because it's a minus, but we're only going right by 3/4. Remember earlier our guess was that this was a horizontal shift right 3? It's not. It's actually only a horizontal shift right by 3/4 because we have taken out of consideration what that compression does. Okay? And then what does this plus 2 do on the end? Well, since it's outside of the absolute values, that's going to cause a vertical shift. And since it's plus 2, that means this is going to go up 2. Now I want to show you one alternative here. When you're actually graphing these, and this one doesn't ask us to graph, but sometimes when you're asked to graph these, graphing horizontal stretches and compressions can be a tricky thing to do, especially when you have lots of other transformations going on. So on this one, what I want you to notice is that the absolute value of this 4 can actually be pulled out. So what is the absolute value of 4? It's just 4 right back again. So one option is that you could pull this 4 all the way outside of the absolute values. The x and the minus 3/4 would have to stay inside. We can't pull those out because we don't know what x is. But if you pull that 4 out, then instead of it being inside of the absolute values, now it's outside, which makes it a vertical change. And since it's a number that's bigger than 1, this would be a vertical stretch by a factor of 4. And that typically tends to be a lot easier to graph than a horizontal compression by a factor of 1/4. Notice that we still have a horizontal shift right 3/4, and we still have our vertical shift up 2. So those haven't changed, but instead of trying to graph a horizontal compression which shrinks everything in horizontally, we can just graph a vertical stretch by a factor of 4 instead. And on an absolute value graph, that's not hard to do because a vertical stretch only affects that pattern. Remember, normally absolute values go over 1, up 1. Well, if we have a vertical stretch of 4, that means you're going to go over 1, up 4 instead. And that's much easier to graph than a compression would be. So a lot of times I will think in terms of vertical stretches and compressions if I can, instead of horizontal compressions or shrinks, or excuse me, horizontal compressions or stretches. Okay, let's try another example. So we have 2 times the greatest integer function of 3x plus 1. So again, before you jump right in here and say, oh, I see a plus 1 off to the or next to that x, so this means I'm going to have a horizontal shift left 1. That might be your first guess. That would be wrong because there's this coefficient in front of your x here, which you haven't correctly factored out yet, and that will affect how your horizontal shift actually occurs. So before you do anything else, you're going to want to factor out this 3 from the x and from the plus 1. Now the 2 on the outside isn't going to get touched. We're going to leave that the way it is. But I'm going to take this 3 and then I'm going to write in parentheses what would be left if I were to factor it out. So I would be left with the x, and then 3 times what gets you back to 1 again? 3 times a third. So you want to put in those parentheses, you want to factor it just like I did here before you start identifying what kinds of shifts are actually happening. So let's start at the front here. What does this 2 do? Since it is way on the outside, that's a vertical stretch by a factor of 2. The 3 on the inside, since it's on the inside, that's horizontal. This is going to be a horizontal, and since it's bigger than 1, we're actually going to do a compression, and it's going to be a horizontal compression by a factor of a third. And then finally, this plus 1/3 that's next to the x, still inside of our greatest integer function, that's also going to be a horizontal change. And this is going to be a horizontal shift. Because it's plus, we're actually going to go left 1/3. So there's a lot of different transformations going on here, and I want to show you graphically on a calculator how you can verify that what we have sort of assessed here as our different transformations are correct. So let's go to our calculator. Let's go to y equals and clear these guys out. And I'm going to type in first just the normal greatest integer function so you can see what that looks like on a calculator. And for the greatest integer function, again, it is hidden, so you have to go to math, and then you're going to arrow over to num, and it's this option 5, this int, that stands for greatest integer function. So hit number 5, and let's hit x. And I'm going to hit graph. And it's going to look a little bit strange from what you might expect, but you do see those little tiny steps here. Now this is a lot of steps, so I'm going to narrow up my window here just a little bit so we can kind of zoom in a tiny bit. So let's go to window, and let's just look at it between -2 to 2 for the x's, and maybe -5 to 5 for the y's. So there's those steps. You can't really see this one because it's lined up right on that x-axis, but there's your step function. Now let's go ahead and change this to our original equation. So we wanted 2 times this greatest integer function. So I'm going to go to math, arrow over to num, and hit option 5. And I wanted 3x plus 1. And let's hit graph. So that's what our graph looks like, and again, you can't really see the one that's in here, but let's try to identify whether or not our shifts look good. Look at your little steps here. You can see this one here and this one here. They have a jump of how much in between them. This one is at 2, this one is up here at 4. So we've stretched them out vertically by a factor of 2. So it looks like we did that one correctly. Horizontal compression by a factor of a third, that looks right as well, because normally the steps should have a width of 1, so it would go from the origin all the way to this little tick mark. But now you can see that these little steps are about 1/3 in length than what they used to be. So it looks like we've done that correctly as well. And then do we have a horizontal shift left a third? Well, this one's a little harder to see because the step lines up. But there is a little step over here on that x-axis, and it's, let me draw the picture over here so you can see it better, but it would be sort of like this. This is what our graph is looking like on the calculator. It's just harder to see this step because it blends in with the x-axis. So this is over at -1/3. So that looks about right as well. We didn't have our first step starting right at the origin and going to the right. It actually, our first step started over to the left a little bit. So it looks like we've identified all of our transformations correctly. Okay, let's try another one here. We have square root of 1 minus x plus 2. Now again, you want to be really careful. It doesn't look like it, but there really is a coefficient in front of this x, namely a negative. So to identify your transformations correctly, you must factor out that coefficient first to identify all of your reflections, your stretches, your compressions, and your shifts left, right, up, and down. So this is how you could factor it out. Think of 1 minus x as negative x plus 1 if you want. You can switch the order around. And what I'm going to do is I'm going to factor out that negative. It's still under my square root, but if I factor out that negative, then what would I be left with in parentheses? I'd be left with just the x, and I'd have to have a minus 1 inside the parentheses so that when I redistribute the negative across, I'd get back this plus 1. And then I have that plus 2 on the side. So these two equations are equivalent. They're just in a slightly different form where this one is considered factored. And the reason that's important is because this negative right here does what? Since it's inside of your square root, that means it's going to be a horizontal change, and if it's a negative, that's a horizontal reflection over the y-axis. The minus 1 on the inside, because it's minus, is actually going to be a shift horizontally right 1 unit. And the plus 2 is on the outside, so that's going to be a shift vertically up 2 units. Now the graph doesn't, or the problem doesn't actually ask us to graph it, but it does ask for domain and range, and sometimes that's easiest to determine by looking at a graph. And I'm going to graph this by hand. So let's go ahead and draw our graph here. We know that we've shifted right 1 and up 2. And normally square roots start at the origin and point to the right. So we're going to take this starting point and we're going to shift it right 1 and up 2. But instead of curving to the right, remember we had this reflection. So instead of pointing to the right and going up and to the right like this, if we're reflecting this over that y-axis, that means our graph is actually going to want to point up and to the left. So if my starting point is right here at 1, 2, I'm going to use my pattern for my square root, but I'm going to use it towards the left. So I'm going to go up 1, left 1, and then up 1, left 3. So it's going to look something like this. So there's my graph. And then looking at my graph, I should be able to see what my domain is. Your domain are your x's, so look left to right. This graph goes all the way to the left, so it's going towards that minus infinity, but it stops at an x value of 1. And it actually hits that 1 with a solid dot, so I'm going to use a bracket around the 1. Then for the range, we want to think up and down. So how low does this graph go? It doesn't go any lower than a height of 2, and it actually hits that 2 with a solid dot, so I want to use a bracket. And then the graph slowly rises up from there and keeps going. So this is going to go to infinity. So there's our domain and our range. Okay, the next one here is a quadratic equation, negative 2x squared plus 4x. And we want to identify all of the different shifts that are going on. But in order to do that, you need to put it into that highly factored form. Remember that this is supposed to look like sum A, parentheses, x minus or plus a number, quantity squared plus k. That's kind of that vertex form of a parabola. So we want to try to get this into that kind of a form with some parentheses put in so that we can identify what's my shift left or right, what's my vertical stretch or compression, what's my shift up or down. So in order to do that, we need to take this quadratic equation right here and we need to put it into its factored form. Now, how do you do that? Well, that process of taking some terms like this and putting it into this factored form is called completing the square. So that's what we're going to have to do here. Now, the -2, that's that coefficient of that x squared term, that is going to turn out to be my a out front here. So the very first thing we're going to do is we're going to factor out the -2 from both of these terms that have x's. So I'm going to pull out that -2, and that would leave me with just an x squared. And what would the coefficient have to be in front of this x term so that if I were to redistribute, I would get back a +4? Well, it's got to be a -2, so that -2 times -2 would give me back +4x. I'm going to leave a little space here, and you'll see why in a moment. So first thing I want to do in this process of completing the square is you have to get the coefficient of the x squared term to be a 1. So if it already has a coefficient, you need to factor that coefficient out from all of your x terms, like we did right here. Once you've done that, what you're going to do is figure out what this needs to convert into in its factored form. And the way to do that is to take 1/2 of this middle coefficient, this coefficient of x. What would be 1/2 of -2? It would be -1. So what this needs to factor into is an x minus a 1 quantity squared. And let's see why that would work. What do you get when you square out x minus 1 quantity squared? If you FOIL it out, you're going to get an x squared. You're going to get a minus x. You're going to get another minus x, so you'll get a total of a minus 2x. And then you'll get a +1 on the side. So what we're trying to say here, let me get this out of the way for a moment, is that if I were to FOIL all of this out, I would get an x squared. I would get a minus 2x. But what I would also get is a +1. And if I did have all three of those terms, that would turn into this x minus 1 quantity squared. However, we didn't have a +1 on the side, so I can't just add it in there. I have to balance it out by also subtracting 1 as well. So we're really just adding a fancy 0 here on the side. The +1 I'm using in this factored form. The -1 is still inside of these brackets for with that -2 way out front. Okay, so this is a little bit tricky, but the +1 gets absorbed into these parentheses squared. The -1 is still inside the bracket because in my last step what I'm going to do is distribute this -2 across, which all it does in the first set of parentheses is gets put in front of that x minus 1 squared, but it's also going to get distributed to that -1 and give me a +2. So what I really did from here to here was get rid of the brackets. So I distributed the -2 in front of the parentheses squared, and then I distributed the -2 to the -1 to get a +2 on the outside. And if you're not convinced, you could FOIL this out, distribute your -2, add in the 2, and you would get back this original polynomial. So it's a complicated process, this completing the square. First you factor out that -2, then you take half of this middle coefficient, and that's the number that's going to go in the parentheses squared. Figure out what the constant needs to be on the end, add it and subtract it within the brackets, and then distribute that -2 across and simplify. Now the whole reason we did all of this is so we could then realize that this right here is going to cause us a certain kind of vertical stretch and reflection. This is a shift, and this is a shift. And we wouldn't be able to identify what those are without having converted this original polynomial into this factored form. So let's identify. What does the negative do? Well, it's outside, so that's a vertical reflection. And if it's a vertical reflection, that means it's going to be over the x-axis. What does the 2 do? It's also on the outside, so it's a vertical stretch by a factor of 2. What does the minus 1 do? It's inside of the parentheses, so that's a horizontal shift. Since it's a minus 1, we're actually going to go right 1. And finally, what does the plus 2 do? It's on the outside, so that's a vertical shift. And since it's plus, we're going to go up 2. So essentially, if you were to put all of these things together, this would be a parabola that has its vertex shifted right 1 and up 2. So right 1 and up 2. And it's a parabola that's pointing down because it has a reflection over the x-axis, and it has a stretch factor. So we'd go over 1, down 2 on either side, and then over 1, down 3 times 2, which would be 6 on the left and on the right. So you'd get a skinnier looking parabola that points down. My graph is a little crooked here because I don't have much accuracy with my pen, but it would be a parabola that's been shifted to the right and up, flipped over, and stretched. Okay? So practice that completing the square. That's a typical example, and it's a little tricky to do. Okay, the next example that we're going to look at is also kind of tricky as well. This one doesn't seem to give us very much information, but what we know is that we have some function f of x, and all we know about it is that it contains the point 4, negative 1. So based on that information alone, we want to figure out what must be on the graph of f of 2x minus 3. And I'm going to show you 2 ways to do this. I'm going to show you one way in terms of just thinking about transformations, and then I'm going to show you another way that thinks about it using function notation. So let's first talk about our transformations. If you were to see this function notation, the 2 on the inside means that that causes a horizontal, since it's on the inside, and it's being multiplied, so that's going to actually cause us to compress because 2 is bigger than 1. Going to give us a horizontal compression by a factor of a half. That's what multiplying x by 2 does. And that's just going to affect the x. So, in this point right here, what's our x value? 4. And what we're going to do is we're going to compress that x by a factor of a half. So what would 4 turn into? What's half of 4? That would be 2. So our new x value is going to be 2. Okay? So that's how we figure out our x. Now we had another type of transformation as well, and that was from this minus 3. And this was on the outside. So it is a vertical shift down 3 units. And because that's on the outside and it's vertical, that affects the y's. So what's the original y value of our point? It's negative 1. And what are we doing to that negative 1? We're shifting it down 3, so we're subtracting 3 from it. So what does this new y become? It becomes negative 4. So if we put this together, then our new point is going to have a new x value of 2 and a new y value of negative 4. So 2, negative 4 must be on this new graph. So that's one way to think about this using shifts and compressions and all those different transformations. Let me show you another option here as well. If 4, negative 1 is on this function, let's think about that in function notation. That means the x value is 4 and the function value is negative 1. So this would say f of 4 has to equal negative 1. So if we want to know what f of 2x minus 3 is, here's what I want to ask you first. What x must we use, or do we need, to make f of 2x equal f of 4? Since the only thing we know about this function is what happens at 4, what x would we have to use to get to f of 4? So what would the answer to that question be? What does x have to be to make 2x turn into a 4? We would need x to be 2. So that 2 is the same as the 2 that we came up with, thinking in terms of a horizontal compression. Okay, so now we know what x needs to be. So let's let x be 2, and I'm going to plug it into this formula. So I'm going to plug it into y equals f of 2 times 2 minus 3. So I'm just letting x be 2 right here in that formula. And I'm going to figure out what y needs to be. So y should be f of 4 minus 3. And what is f of 4? We know what f of 4 is because f of 4 was defined to be negative 1. So substitute in negative 1, subtract 3, and that simplifies to a negative 4, so that means y must be negative 4. So doing it in a slightly different way, we still end up with 2 for x and negative 4 for y. Okay, let's try another example. So this time, again, still using the point 4 comma negative 1, what would the point have to correspond to on the graph of 3 f of x plus 1 minus 2? So let's identify our shifts here first. Which of these shifts are vertical, or which of these transformations are vertical transformations? Let's list those out first. Well, we know the 3 is on the outside, and that causes a vertical stretch by a factor of 3. And the minus 2 is on the outside as well, so that's also vertical. So that's going to be a vertical shift down 2 units. Now both of those are vertical, so both of those affect y, because vertical is y direction. What does this plus 1 do? The plus 1 is next to the x, so that's horizontal, and that is, because it's a plus 1, that's going to cause a horizontal shift left 1 unit. And because that's horizontal, that affects your x. So we have 2 things affecting our y, and we have 1 thing affecting our x. So let's do the x first. The original x was 4. So if we take 4 and we shift it left 1, then that means the new x is going to be 3. So there's our new x value. Now let's take our y. Our original y was negative 1. And what are we doing? Well, first we're stretching it vertically by a factor of 3. That means multiplying it by 3. So that makes the new y negative 3 for the stretch. But we also have a shift down 2, which would just take that y value that we just got and shift it or subtract from it 2 units. So now the 2 makes this a minus 5. So we have the stretch, which made it negative 3, and the shift down, minus 2. So the whole end result is that the y value is going to be minus 5. So our new point would have an x value of 3 and a y value of negative 5. Okay, let's try this using that function notation again. So we know that f of 4 equals to negative 1. So if we're going to use that fact, we need to work with this f of x plus 1, and we need it to equal f of 4 somehow. So what x makes x plus 1 equal to 4? Well, that would have to be x equals to 3. So that's how we determine what our x is. Once we know what x needs to be, let's plug it in to this whole equation over here. So if I plug in x equals to 3 into this equation right here for x, this would become y equals 3 f of 3 plus 1 minus 2. Now by choosing x to be 3, 3 plus 1 gives me 4, and that's important because the only thing I knew about was what f of 4 was. What is the value of f of 4? F of 4 was negative 1. So I'm going to substitute in a negative 1, and then that gets multiplied by the 3, which is negative 3, and then that gets subtracted by 2. So the end result is negative 5, so y must be negative 5. So x is 3, y is negative 5, and that is the same point that we got over here. So I don't care how you do it. You can do it thinking in terms of transformations, or you can think of it in terms of function notation. Okay, our last example. Here is a graph of a function f, and we want to transform it and graph the new function negative f of x plus 2. So to do this, let's identify what transformations are in this formula. The negative on the outside is a vertical reflection, and since it's vertical, that's going to flip us over the x-axis. And then the plus 2 on the outside is a vertical shift up 2 units. So we need to take each of these points, we need to reflect them over the x-axis, and we need to shift them up 2. Now both of these are vertical changes, so that means we're just changing the y values. The x values are not going to change. So this is how I like to do these problems. I just start on the left side and I look at all these sort of important points. So for example, this point, this point, this point, this one, this one, this one, and this one. I'm going to move all of them according to these transformations and then connect the dots. So this dot right here, first I need to do the reflection because reflections rank higher than vertical shifts do since it's a multiplication instead of an addition. So first we're going to reflect this over the x-axis, which would initially move it to here, but then we need to move that up 2 units, so it's going to end up right here. So let me erase some of these other things. That's the end result of that point. Now let's move to this dot. It's at a height of 0, so when I reflect that over the x-axis, it doesn't move. It's going to stay right where it is. But I need to shift it up 2 units, so it's going to end up right here. Notice I'm not moving the x-coordinate at all. I'm just changing the y's, the heights. So since these 2 points were connected with a straight line, so would these 2 points. Now let's go to this little hill right here. If I reflect that over the x-axis, it's going to move to here, and then we have to shift it up 2 units, so it's going to end up right here. If I go to this point over here, it's at a height of 0, so when I reflect it, it doesn't move, but it does get shifted up 2 units, so it's going to end right here. So we have this sort of semicircular shape between these 3 points. I want to maintain that semicircular shape between these 3 points. Let's go to this point. When I reflect it over the x-axis, it goes to here. And then when I shift it up 2 units, look at where it ends up, right back where it started. So between these 2 endpoints was a straight line, so between these 2 is a straight line. This point is at 0. When I reflect it, it doesn't move, but when I shift it up 2 units, it ends up here. And this point, when I reflect it over the x-axis, it goes to here. And when I shift it up 2 units, it ends up here. And all 3 of these points were in a straight line, so all 3 of these are in a straight line. So this graph in red is g of x. Okay, that's a lot of information in one lecture, a lot of information about transformation. So don't forget to review your summary of transformations and your function library. And make sure you know all of those graphs, be able to graph these by hand, and identify all of your different transformations as well. Okay, on these last two examples, we're going to take a look at some new kinds of transformations dealing with absolute values. On this first example, we have the graph of f given to us right here, and what we want to do is create a new function g of x, which is the absolute value of this function. Now here, notice the absolute values are on the outside of the function f of x. And f of x is the same as y. So this is like taking the absolute value of the y values only. We're not going to touch or change the x values at all. We're only taking the absolute value of the y values. So what that means is if I look at this point right here, which has an x coordinate of -5, that's not going to change. But the y value is -2, and the absolute value of -2 would turn into a +2. So instead of being graphed down here, we're going to flip it up and now plot it at +2 instead. So this is like a point that's now been reflected over that x-axis. If we look at this point right here, it has a y value of 0, and the absolute value of 0 stays 0. So this point doesn't move at all. This point up here has a y value of 2. The absolute value of 2 stays 2. So this point doesn't move at all. This point has a y value of 0. Absolute value of that stays 0. So it stays the same. This point down here has a y value of -1. In absolute value, that's going to turn into a +1. So this point, which was below the x-axis, now flips up above the x-axis. This point in the middle is at 0. Absolute value of 0 stays 0, so it stays put. Down here, we're at a y value of -2. In absolute value, that becomes +2. This y value is 0, so that's going to stay 0. This y value is 2, in absolute value that stays 2. This y value is 4, so in absolute value it stays 4. And this y value is 1, so it stays 1 as well. So if we look at our graph here, the only parts of this graph that really changed are the parts that were below the x-axis. I'm going to circle these in yellow. And each of those got flipped over and reflected over that x-axis. Everything else that was above the x-axis to begin with, so that it had a positive y value or a 0 y value, those stayed exactly the same. But anything that was below the x-axis got flipped up. Okay? So when you see the absolute value around the outside of your function, just turn all of your y values into positives or leave them 0 if they were already 0. Now the last example we're going to do is quite tricky. This one we're going to put the absolute value around the inside of our function, in by that x. So here we're taking the absolute value of the x's first and then applying our function to that. And this is kind of complicated and gives students a lot of trouble. So to help us out with this, what I did is I created a table of values here that represent all of our key points on our graph. And what I'm going to do over here in red is create a new table that represents the new points that we want to plot. So what we're going to do is we're going to start our table here, and I'm going to start with my first x value, which over here on the left was -5. Now if I take -5, what we need to do here in order to find this new function g is first we take the absolute value of that x coordinate. And the absolute value of -5 is +5. And now what we want to do with that absolute value is then input that into our function. So we're not inputting in -5 into our function, now we're inputting in +5 into our function. And what does the function give us if we use 5 as the input? Well, if we look at our table here, when we use +5, the output that we get from the function is actually a 1. So this output is going to be a +1. So instead of plotting -5, -2, which would be this dot down here, now we're plotting -5, +1, which is now going to be up here. So we took the absolute value of the x first, and then we looked at what that x value gave for the y value. Let's try it again. So now if I try an x value of -4, we have to take the absolute value of that x value first, which turns it into a +4, and now we refer to the input 4 and use the y value that corresponds to that, which in this case is also a 4. So we're going to plot -4 for the x, because that's the x we originally started with, and then after we're taking the absolute value of that and plugging it into our function, we get +4 back again. So this point at -4 is actually going to be plotted up here at +4, -4, 4, and -5, 1 were our first 2 points. Let's try it again. Let's let x be -3. So according to this, you want to take the absolute value of your x first, which is going to turn this into a +3, and then you want to use that as your new input into your function f. And according to our function, if the input is 3, the output should be 2. So our new coordinates are going to be initially a -3 and with a new output now of +2. So that is actually this point right here. Let's try the next one. If x is -2, in absolute value that becomes a +2, and what is the function at 2? Well, when the input is 2, the output is 0. So I'm going to be plotting the point -2, 0, which happens to be this point right here. Let's move on to the next one, -1. So the absolute value of -1 turns into a +1, and what is the value of the function at +1? Well, the input is 1, the output's supposed to be -2. So we're going to plot -1, -2. So that's actually going to be down here. All right, let's go to 0. If I use an input of 0 for x, the absolute value of 0 stays 0, and the function value at 0 is also 0. So this is going to be 0, 0, right at the origin. Now let's try some positive inputs to begin with, some x's like +1. If x is 1, in absolute value that's going to stay 1, and the value of the function at 1 was -2. So we're plotting 1, -2, right down here. If I use an x value of 2, the absolute value of 2 stays 2, and the value of the function at 2 is this 0. So we're plotting 2, 0, right here. If I use 3 for x, the absolute value of 3 stays 3, and the value of the function at 3 is 2. So we're plotting 3, 2, right here. If I use 4 for x, the absolute value of 4 stays 4, and the value of the function at 4 is also 4. So we're plotting 4, 4 up here. And finally, if I use an x value of 5, the absolute value of 5 stays 5, and the value of the function at 5 is this 1. So we're plotting 5, 1. So if I connect the dots, this whole right side of the graph did not change at all. It's exactly the same. The left side, look at what shape it has. Let me darken it in here. What do you notice about this graph? It's a reflection over the y-axis. We did not use any of these points over here at all. We lost all of those. And instead, we just plotted the positive or 0 x values and their corresponding y values twice, once on the right side of the y-axis and once on the left side of the y-axis. So what you want to remember about an absolute value around your x is you keep the right-hand side of your graph exactly the same. You just recopy it. That's not going to change. And then you reflect that whole graph over the y-axis over here to the left side. in quadrants 2 and quadrants 3. So your graph should be a mirror reflection over that y-axis. So you keep the original graph that's over here on the right side reflected over the y-axis to get the graph on the left side, and you lose the entire part of the graph that you originally had on the left side. That whole shape just disappears and goes away. So this one's kind of a complicated one to do, but it's basically just keep the right side and reflect it over that y-axis. Alright, that concludes our video lecture on transformations. Good luck!